you can do all sorts of neat things with AI. One of them is to run a tractor and a lot more. So can you tell us a little bit about the technology that John Deere has been developing?
Absolutely. So Blue River Technology is a company that's owned by John Deere, and we've specialized in deep neural networks and robotics. So being able to have machines that sense their surroundings and do better work. The two examples we have of this are See and Spray, which is 36 cameras on a 120-foot wide sprayer boom that detect the crop, detect the weeds, and spray only the weeds. Right, so that gives farmers like a 60% reduction in their herbicide bill. Another one is autonomous tractors. Same exact types of technologies, right? Where we have, NVIDIA GPUs on the edge, deep neural networks trained with hundreds of thousands of images, and now you can have a tractor that can autonomously run day and night while farmers do other tasks that are important on the field. So they just can set this machine up. It does hours and hours and hours of work for them, and then they come back and pick it up. So it's really fun.
Now, this sounds a lot like some self-driving cars, but
Totally.
How does that differ from what you're doing, and what were some of the advantages you may have had because of the constraints that you could place on the system?
Totally. So I came from a self-driving car background, and what I loved about these outdoor utilitarian jobs like farming is that number one, you can stop. So if you ever think you're wrong, if the system has low confidence, if the system thinks it's detected an anomaly, it can just stop. Whereas on a car, you're going 60 miles an hour on the highway. If you stop, someone could rear end you, and if you don't stop for something, you might hit something. So in on-road, even if the environments were totally the same in terms of complexity, not being able to stop when you lack confidence is puts an incredible amount of pressure on the quality of the system. The other dimension is just the much simpler environment, right? If you go to a farm, any farm in America, and you stand around and look around, you're going to see really three things. You're going to see ground, trees, and sky. And occasionally see some buildings, occasionally see some cars, and very rarely do you ever see people. What that does is allow us to really train to that environment, right? Where we can get very, very good at detecting ground, trees, skies, trucks, houses, these kinds of things. And when we find something that doesn't quite fit into that, we know that's some kind of anomaly, right? And we know, hey, we should stop for that, right? And so it makes just the whole training pipeline much easier. You don't have to think about as many edge cases. And then on top of it, our speeds are just slower, right? Every time you go faster, it means you need to see further. If you're going to see further, it means you need to process more pixels. If you need to process more pixels, you need to do it faster. So speed puts pressure on your sensing. You have to be able to see further better, so your sensors just have to be better. And then you have to process more pixels per second or more LiDAR points per second, which then makes your compute blow up.
Right.
So you have, in self-driving cars, often these computers, liquid-cooled computers that fill the trunk, whereas ours are kind of the size of a deck of cards, right? Because we're going, 15 miles an hour, not 75 miles an hour. You kind of add all these things together, and it just becomes a much more tractable problem. You can get to market, with R&D budgets 10 to 100x smaller than what you'd get to in the self-driving world. Still hard. It doesn't make it easy. We have a hardcore deep learning research team that is stretched to their limits on a daily basis to truly make a quality product that a normal, untrained farmer can just use. The quality has to be very high, but I think just given all these advantages we have in the environment, it's just tractable on a shorter timeline and with lower budgets.
Well, the nice thing is you now have this in production.
Yep.
The challenge, I think, in the future is how you potentially either going to improve this or potentially scale things down into smaller implementations. Because for the most part, these are relatively large tractors and things that you've implemented the first version on.
Sure. So first, the way we've developed is we start with we call it an ODD, operational design domain. So kind of in autonomous systems, you think of the environment that's going to describe where your system can operate. Is it foggy? Is it rainy? Is it night? Is it day? Like all these variables are called the operational design domain.
Right.
So what we start with is the smallest possible one that creates value, right? And so we shrink down everything. We say, okay, it's day only. Okay, it's soybeans only. It's this one part of the Midwest only, and it's only these 5 customers. And you really make your ODD incredibly small, build an end-to-end system, prove that the core technology works, and prove that it has value, prove people will pay for it before you go and kind of scale your way through the rest of the ODD. And once you're convinced of that, and we have high conviction of that, what you actually start doing is just expanding through that ODD, and that's your product roadmap, where it's like, cool, now let's make it work at night. Now let's make it work closer to telephone poles. Now let's make it work in dustier conditions. Now let's make it work at higher speeds. Now let's make it work in corn. Now let's make it work in cotton. And your kind of market size grows and grows and grows and grows and grows and grows. Now, eventually, let's say we saturate all of agriculture for large agriculture. Well, there are orchards. John Deere makes all kinds of different equipment
Right.
in all kinds of different industries. We make farming equipment, we make construction equipment, we make forestry equipment, we make lawnmowers. And every one of these machines shares these same characteristics. You can stop, it has a simpler ODD, highly utilitarian use case, labor shortages that are driving adoption of automation and autonomy. And so the problem isn't how do we scale, it's how do we choose what to scale.
Okay.
There are so many opportunities to scale that's we do spend a lot of time arguing, should we go A or B? So
Now, the planting system that you have in place is very impressive. It actually, gets the trough where you're going to be dropping the seeds in, drops them very precisely, adds fertilizer to it. How many different cameras, AI models are being used for each one of the different steps?
So there's a bunch of different components in planting. Right. You have that clearing wheel, the trench opener. Right now, we've got a product called Furrow Vision that we're using to basically, for the first time, like have a camera in the trench, viewing those trench walls. It's been a little bit of an adventure, actually, because we didn't really know what the insides of the trench looked like because it gets open and closed really quickly. And so that environment has never been well understood by mankind. So it's kind of like putting a camera somewhere where no camera has ever been before. So the first step we did was just observe that environment, and now we're kind of going through, okay, what do we actually have to detect? What models do we have to build in order to detect, seed placement? Like where is the seed? What's the seed's orientation? What does the surrounding area look like? Is it a cracked wall? Is it a smooth wall? Is there other debris in the wall that could get in between the soil and the seed? So these are the kinds of models we're going to start building there. A lot of the rest of the stuff is actually just like pure automation and timing. So it's like high-speed electronics and timing. It's kind of sense that, so GPS is sensing our speed. We have this wheel that shoots the seed backwards at the exact same rate the tractor's traveling forwards, so that the seed bounces vertically. Because there is sometimes bounce in the seed, and if you've got the seeds bouncing along the line, they'll bunch up together. If they bunch up together, they fight for resources. If they're too far apart, you've wasted land and valuable resources. So typically we run, what we try to do is have as few cameras and as few neural networks running that do the most possible things. And kind of still figuring this out in the planter.
Well, speaking of figuring things out, are things like the type of soil that you're dealing with, the amount of moisture,
100%.
Those all factor into what's being used?
Absolutely. It's it is there are an incredible number of variables in the soil. Some of them you can observe with the naked eye. So an RGB camera works. Some of them, like moisture, you could infer from the naked eye based on color and other things. Some you could not infer from the naked eye, and many you'd need a mass spectrometer to truly understand the constituents and the nutrients inside the soil. So there's this huge range of things to truly understand the soil. And the soil is like, you can think of it as it's like a battery of nutrients, right? And the seed's going to draw from those nutrients. The plant's going to draw from those nutrients and draw it down. And one of the challenges farmers face is actually, you never know how much that battery's charged, right? And so imagine if you have an iPhone and it didn't have an output on how much it was charged, you'd just charge it all the time.
Yes.
Right? You'd go like every few hours, you'd be like, I might run out of charge. I don't want to run out of charge. And so you'd plug it in. And so that's a little bit what happens in farming, is where people don't know, they don't always take core samples and figure out, what their nutrients are like. So they over apply nutrients, which is wasteful. Anyway, so there's a huge opportunity in this, in better understanding content of soil and the nutrients in the soil. It's a challenging problem.
Okay. One of the things that NVIDIA has been doing is essentially improving the software, giving you more performance without upgrading the hardware.
Yeah.
Are you finding that to be advantageous in terms of adding new features to your
100%.
applications?
Yeah, NVIDIA has been an extraordinary partner. They gave us early access to their Jetson platform while we were still a startup. We built our first deep learning prototypes with it. Every new jetpack that comes out usually comes with, frankly, a bunch of integration problems followed by some awesome performance improvements. They are on, a lot of this would not be possible without NVIDIA. And it's just an extraordinary platform they built where it's thermally efficient, it's power efficient, it's right size for our applications. Absolutely, there's software tools. Some of them that prune models that basically can help you optimize models and go to, int 8 rather than int 16 to make them run faster. Like all of this tooling we use, and it helps us extraordinarily.
Okay. Now, in terms of the optics, are you using standard cameras? Are you using time of flight type cameras? What you need at this point to get all of that information about the soil, the position of the seeds, and so on?
We kind of we're non-dogmatic. We use what we need. One of the things we think of, like, sensors are like sneakers. It's like, just because you have Steph Curry shoes doesn't mean I can be as good a basketball player as Steph Curry. So most of the anyone can kind of buy these sensors, but I think the value is in what do you do with that, right? But that said, we do have some pretty incredible sensors. Probably the best example is on See and Spray, we use RGB NIR, so near infrared, and you can basically detect plant matter, like very, very reliably. It very much pops out relative to the background. That's a custom camera we built. The stereo camera that we use on the autonomous system, one of the problems with stereo cameras is that the pose, if you get small misalignments in the pose of one of the cameras, you get these massive angular errors that stack up and basically give you poor depth prediction, right? So the physical robustness of this system is extraordinary, and really Blue River never could have made this. John Deere made this extraordinarily robust stereo camera. We've actually gone a step further, where we bought a company called Light about a year ago. And what they're doing is, so one of the downsides of stereo cameras is, so in theory, the wider and wider and wider you make your baseline, the better and better and better you see depth at further and further range, right? Right. With maybe a little bit of sacrifice of ability to detect depth in close up, but that doesn't matter as much. In real life, you run into kind of material science and mechanical engineering limitations. So the further and further and further apart you put these cameras, throw a vibrating diesel engine on there, and these cameras actually start to waggle relative to each other, and their pose relative to each other changes slightly. Those angular errors stack up. So what you have in real life is, if your x-axis is distance between cameras and your y-axis is depth performance, you'll get a peak, right? You'll hit a max, and then you'll get diminishing returns the wider you make it. And so we bought this company called Light that helps alleviate that, where you can actually put cameras extremely far apart. We'll have double overlap, so triple overlap of every camera. And what happens is those things naturally move around relative to each other, and we're calibrating the pose of each camera on a per frame basis, right? And so we can kind of live with these, we can live with that mechanical slop, So rather than make the most robust possible camera, we're like, well, just put them on there in roughly these positions, and we'll work it out in software. That gives us kind of LiDAR quality depth with camera cost and camera robustness. And so, we do use LiDARs a little bit for various projects, and sometimes we use them to train depth models. So you can, you ever heard of depth from mono?
Yes.
Yeah, so you do depth from mono type activities. We use it to ground truth, stereo cameras. We use them more kind of in R&D settings to ground truth things than in production settings. I think they're going to be robust enough for agricultural production, but moving parts tend to be pretty tough in ag, moving parts are trouble. And so anyway, we've made a lot of use out of cameras and deep learning and other techniques, but mine's always open for whatever's out there.
Well, obviously these are being used outdoors,
Sure.
rugged environment. What's the challenge you usually have on maintenance of this stuff?
So this is why we want as few moving parts as possible. Right now, the maintenance is occasionally you'll have to go and dust off the lenses.
It's excellent. Yeah. So where do you see this going in the future? Are we at the point where everything is sufficient and it can be just static, or are we going to see more improvements?
Across the board, we're just at the beginning. I would say we're at the beginning of the beginning. We're at the point where we've had all these ideas for years and years and years, and actually getting them through to production. Partnering with an OEM who's, Deere's just been an awesome parent company, where there's not a lot of successful cases of OEMs and Silicon Valley companies partnering. We have one of them, and we've proven it by shipping a few products together, and what it is more and more performance in more and more environments. I mean, one of the ones was See and Spray. Right now we're spraying meter by meter patches, right? And we actually think we could get down to centimeter by centimeter patches, right? And if you can get down to centimeter by centimeter patches, well, you may not need GMO seeds. Because you're not spraying any herbicide on the crop at all, right? So that could 10x reduce seed costs for farmers. We've not touched construction, we've not touched forestry, we've not touched lawn mowing. I mean, it is sort of a room full of piñatas of opportunity, and we've only gotten through 2 of them, and really only gotten to the early markets in 2 of them, and are just beginning to scale those 2.
Well, excellent.
Thanks.
Thanks for filling us in on what's happening at John Deere and out in the fields.
Thanks so much. Take it easy. That was fun.
Thank you.